Okay, so yesterday we looked at comparing and ordering rational numbers. Today we're going to go one step further and look at compare and order real numbers. So real numbers include rational and irrational numbers. So just a reminder about that. So the set of real numbers is all rational and irrational numbers. Remember, irrational numbers that are not repeating, they are not terminating decimals, they never end, they never repeat, and you cannot write them as a fraction. So go ahead and get those two terms down. Now, the good thing is when we are comparing these types of numbers, we're going to do it very similar to how we did it yesterday. And I will also say that I'm going to show you how to do this without using a calculator, because you're going to be asked throughout the school year to be able to do these types of problems without a calculator. So we're going to use a couple of different methods and techniques to figure that out. But first, write all the decimals and fractions in the same notation. Like we did yesterday, make them all decimals, make them all fractions, most all as decimals. Write all percents as decimals as well. And then we're going to use our perfect squares. Remember, perfect squares are those numbers that we can find the square root of. And we're going to use them as what I like to call checkpoints. So think about with a video game. You like to play video games. You have what are called checkpoints. Checkpoints, what are they? Well, they're places that if you were to die or lose in that video game, you would go back to that checkpoint. So you want to cross the checkpoint so that way you can go back there if you need any help or if you need some assistance or if something were to happen. Checkpoints, you know where they're at because you try to get to the checkpoint before you end up losing or dying or whatever. Well, checkpoints in this lesson are going to be used very similar. So you've got underneath checkpoints. First of all, what I want you to write up at the top is use perfect squares to estimate. And I want you to draw a number line going the entire way across your paper. So a number line that goes the whole way across. So on our number line, we first obviously start with 0. Okay, we're going to go all the way to 4. Actually, I'm going to put 5 on mine as well. I got room. So like I said, we want to use what we call these perfect squares to estimate for these checkpoints. So 1 is the square root of 1, right? So 2 would be the square root of 4. 3 would be the square root of 9. 4 would be the square root of 16. And 5 would be the square root of 25. So we're going to fill in some of these other square roots that we don't know that are irrational numbers, but we're going to be able to do that and know where they're close to because we know these perfect squares. So what about the square root of 2? Well, the square root of 2 is in between the square root of 1 and 4, so it's somewhere close to here. It's closer to 1 because 2 is closer to 1 than it is to 4. But also there's another square root that would be right around here, which is close to 2 or the square root of 4. And that would be the square root of 3. So notice we've got the square root of 1 is 1. The square root of 4 is 2. So in between the square root of 1 and 4, we have the square root of 2 and the square root of 3. So let's look in between 2 and 3. We've got the square root of 4 and the square root of 9. So that would be the square root of 5, 6, 7, and 8. Now, they might not be exactly spaced out like what I have up here, but you know that the square root of 8 You don't know what that is without a calculator, but you can estimate. And you can say, I know the square root of 8, it's going to be close to 3, but not quite 3. Because the square root of 9 is equal to 3, and 8 is really close to 9. So the square root of 10 would be even closer to 3, actually. And what's another irrational number that would be really close to 3? Another irrational. That would be pi, right? Pi is 3.14. So pi is an irrational number that is close to 3. What about the square root of 15? Where would the square root of 15 go? Put that on your number line if you think you got it. The square root of 15 is not quite to 4 because 4 is the square root of 16. So it's going to be somewhere around here. So then what's going to be on the other side of the square root of 16 or 4? Well, that would be the square root of 17. What about the square root of 20? The square root of 20. Well, that would be somewhere in between 4 and 5, right? Because 20 is pretty close to in the middle of 16 and 25. So the square root of 20 right in the middle there. So that is what I'm talking about when I say use your checkpoints. Your checkpoints that you're using are all those perfect squares. The square root of 1, the square root of 4, the square root of 9, 16 of 25, go up one more, 36. Those are your checkpoints. So the ones that you know the answer to without a calculator, you know these squares because they're perfect squares, those are going to be what we call our checkpoints. So the way that we use our checkpoints is as follows. We've got the square root of 7 or 2 1/3. So go back to this last one, the square root of 7. That was close to what? Well, it was in between 2 and 3, but it was closer to 3. So I'm just going to write here square root of 7 closer to 3. 2 1/3 would be 2 point, and then 1/3 as a decimal, remember, is 3 repeating. So if you want to look at a number line, 2.3 repeating, that would be somewhere right here. Well, that's obviously going to be less than the square root of 7. And so the square root of 7 would be greater than 2 1/3. Okay, let's look at our next example. 15.7%. Remember a percent, you want to move your decimal point 2 spots to the left. So 15.7% would be 0.157. And then 0.4 squared, that is 0.4 times 0.4. Well, 4 times 4 is 16, and we need to move our decimal point 2 spots to the left. So it would be 0.16. Well, what's bigger, 0.157 or 0.16? 0.16 is going to be bigger than 0.15. So 0.4 squared is greater. And then the last thing we'll have to do is order these sets. So I'm going to go right here. We're going to do what we did yesterday. Okay, so remember yesterday we wrote all those numbers as decimals and we compared each place value. So I've got the square root of 30. Now, we don't know as a decimal what the square root of 30 is. But look back here. The square root of 30 is going to be in between what two numbers? It's going to be in between 5 and 6, right? Okay, because we've got the square root of 30 that's in between the square root of 36 and the square root of 25. So between 5 and 6. Let's say it's going to be right around 5.5. We don't know that for sure, but just kind of estimating it'll be close to 5.5. Then let's do the same thing. So we've got 6, which is 6.0. 5 4/5, which would be 5.4 is 8. So So 5.80, and then 5.36 repeating. That 6 is what's repeating. So looking at those four numbers, now that we've written them out, what would be the smallest number? I think the smallest number would be 5.36 repeating, right? Okay, so 5.36 repeating. I'm going to cross that off. Next, we've got, I would say, the square root of 30, because the square root of 30 is going to be right in between 5 and 6. It's going to be less than 5.8, which is 5 4/5. And then finally, the greatest number that we have is 6. All right, so least to greatest, those are it. And you're doing this without a calculator because you can use the checkpoints that we talked about, those perfect squares that you know the answer to. You can use those to kind of guess or estimate where everything is close to. All right, so using what we just did, kind of the estimation, you all go ahead and do those three on your own. Pause your video and do those three. Okay, so we've got first two, the square root of 15 and 3 1/3. Well, let's go back to our checkpoint list. Remember, the square root of 15 was really close to the square root of 16, and the square root of 16 is 4. So this is really close to 4. And we've got 3 1/3, which is 3.3 repeating. Well, I would say the number that is close to 4 is going to be greater. The square root of 15 is greater. 302%, our decimal point right now is here. We move it 2 times, we get 3.02. So those are actually equal. And then last thing, remember, negatives are opposite. So let's think of this not as least to greatest, but actually as greatest to least. Okay? Because negatives are opposite, remember? So you have to think about that kind of in reverse. So let's do the same thing. We've got the square root of 60. Now, the square root of 60 is really close to the square root of what? What about the square root of 64? And the square root of 64 is 8. So this is really close. I'm going to say closer to 8 than it is to 7. Because 7 is the square root of 49. Okay? So I would say that's closer to 8. So that's going to be really close to 8. Then we've got negative 7, so 7.00. 62 over 9. You could divide that. That's also 6 and 8/9. And so 6 and 8/9 would be 6.8 repeating, 6.88. And then I've got negative 7.40. Okay, so the smallest number is obviously going to be 6.88 or 62 over 9. But remember, negatives mean opposite. So this is actually going to be the biggest number. So I'll say that's number 4. Okay, the next smallest number was 7, negative 7. So that's going to actually be the next biggest number because we're thinking opposite. These are negatives. And then 7.4 is less than 8. So finally, the number that's closer to 8 is our least number. So going from least to greatest, I've got negative square root of 60. Then I've got negative 7.4. And then I've got negative 7. And finally, I've got negative 62 over 9. Now remember, we had to think opposite for that. Think of it as opposite because it's negative, and negative means it's really thinking greatest to least. So that is how you compare and order irrational and rational numbers without using a calculator. Use those checkpoints. That number line will help. use your perfect squares because you know what those answers are. So go ahead and answer those questions on your own.